All right, welcome back, everybody. We are talking about the last law of Newton's three laws, Newton's third law. Here we go. So, actually, before I go into it, we've often heard that Newton's third law is every action has an equal and opposite reaction, and a lot of physicists don't really love that reaction, that definition, and maybe it's a little bit of an oversimplification, but I think it gets a general thing across. But here's a little bit more specific. Whenever one object exerts a force on a second object, the second object exerts an equal force on the first object in the opposite direction. Okay, and that might seem complicated, but we're going to go through a few scenarios to help us out with this. There is no such thing as a lone force. All forces come in pairs. So I'm going to explain this a little bit more with the next slide. Okay, and if you can watch this, watch it. Great example in space. Okay, when you punch a wall, it hurts because, in a sense, the wall punches back. So this is an example like, okay, when you punch this wall, when this fist comes in and punches this wall, what's going to happen is, yes, this wall is going to feel a certain amount of force by the punch, but your hand is also going to be feeling a certain amount of force from the wall. And those two forces are equal to each other, but in opposite directions. Okay? Fish are able to swim because they push against the water, and the water pushes in turn, and the water in turn pushes back. So if you can imagine, if you're lightly paddling through the water, you're going to lightly move through the water. But if you're fiercely moving through the water, like you see Olympians do when they're swimming, they move very quickly. So the amount of force you put in this situation against the water, the amount the water pushes back on you. When people walk, they're essentially pushing against the ground, and the ground is pushing back. Yes. So, it's a little bit of a weird concept to think about, but when somebody is walking, sorry, not the best person to draw, but what they're doing is they are pushing the floor this way, and in return, the floor is pushing back on them the other way, propelling them forward. Okay. And this is essentially how we walk. If there's no friction on the ground, and you might have experienced this with ice, you're not really going to be able to propel yourself forward because the friction, the floor, is what gives you the direction to go forward. Okay, someone was to shoot a gun. After the gun of fire, there's a recoil that pushes back on the gun. We've seen that in movies all the time, or if you shot a gun. Rockets work by expelling lots of fuel out of one end, which propels the rockets the other way. Yes, so we've probably seen that when we have a rocket here. What we have fuel shooting out this way. And since we're putting a lot of force shooting out this fuel, what it does is the opposite reaction is for the rocket to go the other way. Okay. And we'll be doing more problems to talk a little bit more about this. Okay, some conceptual examples. A large truck is out on delivery. While it is driving on the highway, it hits a bug that splats on the truck's window. In this scenario, which object experienced more force? A, the truck. B, the bug. C, both were the same. So you might, initially you might be like, okay, well, I guess all objects experience the same amount of force when they come in contact, so it must be both were the same. You might say that, and that's correct, but you might be feeling weird. But it's like, what? I don't understand. If they both come into collision, the bug would feel so much more, would get so much more damage than the truck. How do they feel the same force? And that's true. However, what's happening here is the bug has a lot less mass. It has this tiny mass, while this truck has this huge amount of mass. So even though, yes, they both have experienced the same amount of force, when they collide, what's going to be happening is this bug here, since it has so much less mass, it's going to be experiencing a lot bigger change in acceleration. Okay. It's going to hit this car, and it's going to, in an instant, moving this way to moving this way with the truck. While the truck itself, when it hits this bug, it's barely going to be changing its motion. Its acceleration is going to be tiny. So meaning it's not really going to change its motion. So what's happening here is the acceleration is changing a lot for the bug and not so much for the truck, but the force is the same for both of them. Okay, I hope that makes sense. We'll be doing more if it doesn't. When people are batting in baseball, oftentimes when they try to hit a ball but they miss, they may fall or be unbalanced. However, when they hit the ball, this rarely happens. Why is it that when they miss, the baseball player gets unbalanced? Okay, so if you've ever played baseball or if you ever tried to swing hard in baseball, you've probably experienced this phenomenon where you're trying to hit the ball's coming at you, but when you swing, you feel unbalanced and maybe fall to the ground, or you just feel unbalanced. And why is that? So what's happening is, let's say you hit the ball, you're swinging for the ball really hard and you hit it. What happens is the ball is going to be pushing back on you a little bit as you hit the ball forward, and you're expecting that kind of pushback to balance yourself out. But when that pushback isn't there, what you do is you fall. It's the same thing as like when you're like walking downstairs and you're expecting there to be another step, but there isn't, and then you just kind of fall to the ground because you're expecting that floor to push back up on you, and since it's not, you're just kind of like now falling to the ground. Yeah. Anyway, so I have a video kind of showcasing this a little bit. So if you want to watch that, please do. Next one here. Okay, a large truck is out on delivery. While it is driving on the highway, it hits a bug that splashed on the truck's window. In this scenario, which object experienced a larger acceleration? Why? Okay. So we should know that when both these objects come into contact, the bug will feel a force this way, and a truck will feel a force this way. We should know by now that the forces are going to be the same. And we should know that force is equal to mass times acceleration. What we should know is, and I explained this already, but what we should know is even though the forces are the same, the masses of these objects would be different. So again, the bug would have a tiny mass, while the truck would have a massive amount of mass. So if they both experience the same force, but they have different masses, that means their acceleration has to be different. So the bug will have a lot larger acceleration, while the truck will have a tiny acceleration. So the bug would have a larger acceleration, and that's because it has less mass. Okay, and that's also why the bug is going to be damaged a lot more than the truck. Okay, moving on. So even though experiencing the same force, the acceleration experiences is much greater. Okay, when people are participating in tug of war, what reaction forces do they rely on in order to be successful in the sport? So when people are doing tug of war, a lot of people think, oh, you need to be really strong with your upper body, your arms have to be really big. But if you watch professional tug of war people, which there are, you can actually notice it's more of their legs. And essentially what they are doing is they are pushing on the ground. They are pushing on the ground this way as hard as they can, and the ground is pushing back on them. Oh, I should actually draw this differently. Sorry. They are pushing on the ground as hard as they can this way, and the ground is pushing back on them the other way. Okay, and that's essentially what you're trying to do. You're trying to push on the ground as much as possible in the opposite direction, so it can propel yourself to win in the game. Propel yourself to win in the game. And yeah, in my class, sometimes what we do is we do tug of war in socks, and we see how hard it is to do that. While when we put on shoes where there's more friction, it's a lot easier to win in tug of war. And here, there's a video kind of showcasing how this works a little bit. Okay, two people are out ice skating on the pond. Person one is a lot bigger than person two. They decide to meet in the middle of the pond and push off each other. What is true about what these two people experience? A. They both experience the same force and they both travel the same speed after the push. B. They both experience the same force and person 2 would travel faster after the push. C. Person 2 experiences more force, but they both travel with the same speed after the push. D. Person 2 experiences more force and then person 2 would travel faster after the push. So we should know when two people are interacting, when there are two objects, when there's a force acting between interacting between two. They're going to be the same but opposite direction. So we should know that C and D are not correct. Okay, so we're going to say this is person 1 and this is person 2. Person 2 has a lot more mass than person 2. So we should know that even though they're both going to experience the same amount of force, person 2 is going to experience more acceleration, while person 1 is just going to experience a little bit of acceleration. Meaning after the push, person 2, since it's accelerating higher, will have a faster speed. Okay, so it'll be option B. Okay, moving on. Okay, identify the action-reaction forces in the following example and mention the direction force is going. A person kicks a soccer ball to the right. Identify the pair forces between the football and the ball. Okay, so when this person kicks the ball, we're going to say directly to the right, even though it doesn't look like that if you've played soccer. It's going to be hitting the ball to the right. However, when he hits it to the right, the soccer ball is going to be hitting this leg to the left. Okay. Soccer ball will experience a force to the right provided by the person's foot. Person's foot will experience a force to the left provided by the soccer ball. Okay. Identify the action and reaction forces to the following example and mention the direction each force is going. Identify the two pairs of forces with the boulder, person, and ground. Okay, so if this guy's probably going to be pushing this boulder to the right, and the boulder is going to be pushing back on him to the left. This person is going to be pushing on the ground to the left, and he's going to be the ground is going to be pushing back on him to the right. There are also more forces. For example, the boulder is going to be pushing down on the ground. That we're going to call actually that's the normal force, and the ground is going to be pushing up onto the boulder upwards, and that's the normal force right there. And same with the ground for the person. But anyway, it just asks us to identify two, and there are more too, but I don't want to go into it. Boulder experience a force by the person. The person will experience the same force, but in the opposite direction by the boulder. The person will push off the ground to the left, looking at the diagram, and the ground will propel the person forward. Okay. Next one. Identify the action-reaction forces in the following example and mention the direction each force is going. Identify at least two pair forces with the box, rope, person, and ground. Okay. So this person is pulling on this rope here. So how is this going to work? Okay, the rope here is going to be pulling to the right, but also for the rope on this side is going to be pulling to the left. Okay, so that's one. And what's happening here is this box is kind of like resisting motion, pulling on. Oops, sorry. Okay. Another thing is we have the ground. The box is going to be pushing on the ground going down, and then the ground is going to be pushing up on the box going up. Same thing with the person. And also same thing over here. This person is going to be pushing on the ground to the left, while the ground is going to be pushing him to the right. And there are a few more, but anyway, let's see. A person pulls on the rope pulls on the person. Rope pulls on the box pulls on the rope. Person pushes on the ground pushes back. Okay, there's a few more, but not going to get into all the detail of it all. Okay. I believe there's one more after this. Two people are out ice skating on the pond. Person 1 has a mass of 72 kilograms, and person 2 has a mass of 48 kilograms. They decide to meet in the middle of the pond, and person 1 pushes person 2 with a force of 45 newtons. Assume friction to be negligible. What is the magnitude of acceleration each person experiences? Okay, let's say this is person 1, person 2, and I'm going to do mass of this person is 72 kilograms. Mass of person 2 is equal, I'm going to do mass 1. Person 2 is equal to 48 kilograms. And they person, they be in the middle, and person 1 pushes person 2 with 45 newtons. Okay, so this guy gets pushed with 45 newtons. But we should also know each force has an equal and opposite reaction force. So when he pushes him, he actually also gets pushed back with the same 45 newtons. Okay, let's look at person 1 first. I'm going to just circle this. I'm just going to circle person 1. So we know the sum of all forces is equal to mass times acceleration. We're going to look in the x direction because that's where it seems like the net force is going to be. So I'm going to put negative 45 newtons because it's being pushed to the left is equal to the mass 72 times acceleration, which we're looking for. And now I'm going to just put into my calculator negative 45 divided by 72. And we get negative 0.63 meters per second squared. Well, we should know it's asking for the magnitude, so the answer is 0.63 meters per second squared. Okay, change the color right here. Now I'm going to do person 2. Okay, person 2, sum of all forces is equal to mass times acceleration. So we have 45 going to the right. The mass of this person is 48, and we're looking for the acceleration. Then I'm just doing 45 divided by 48, and we get 0.94 meters per second squared. And this should make sense because since the second person has less mass, he's going to have more acceleration. Okay. All right, part B. If person 2 decides to push person 1 with the same force, would the answers to part A be different? No, it wouldn't be different because still this person would be pushed by 45 newtons by person 2, but they both experience the same kind of force because it doesn't matter. When one object is applying a force to the other object, there's going to be equal and opposite on the first object. So it wouldn't matter. Whoops. It would be exactly the same. All right, let's do the last problem for this chapter. Example number 25. Billy decides to invite Tom to go canoeing with some of his friends. Tom is a little worried about this, but decides to go. The two groups of canoeists meet in the middle of a lake. Tom, who is in canoe 1, doesn't like the other people in canoe 2, and he pushes on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is 150 kilograms, and the mass of canoe 2 and its occupants is 250 kilograms. Find the acceleration the push gives to each canoe. Okay, so this is canoe 1. Ooh, maybe I'll use, what color should I use for this? Maybe black. So this is canoe 1. This is canoe 2. The mass of this canoe is 150 kilograms. The mass of canoe 2 is equal to 250 kilograms. And Jonathan here is pushing on this boat with a force of 46 newtons. And this boat, as a result of that, is getting pushed back with a force of 46 newtons. Okay, find the acceleration for both. So let's do 1 first. So I'm just doing sum of all forces is equal to mass times acceleration. So boat 1's going to experience a force in the x direction of negative 46 newtons because it's going to the left. Mass of the boat is 150, and we're looking for the acceleration. So I'm just going to do negative 46 divided by 150, and I get negative 0.31. Negative 0.31 meters per second squared. Let me use a different color for 2. For 2, I'm going to use this light blue. Okay. Sum of all forces is equal to mass times acceleration. The force is 46 newtons. The mass of this boat is 250, so we should know the acceleration will be less. And I'm going to do 46 divided by 250, and I get 0.18 positive. And that makes sense. It should make sense. Okay. Yeah, I read it a little bit, but that's essentially the answers. What speed did each of canoe move after 1.2 seconds of moving? Okay, so this is where it gets a little bit maybe more complicated. I'll go back to black. So number one, we should know there at the very beginning, the initial velocity is zero, just the boats are at rest. It's going to be pushed for 1.2 seconds, and it's going to be accelerating at a rate of negative 0.31 meters per second squared. And we want to see what the speed is after 1.2 seconds of pushing, so we're looking for V final. So I'm going to have the equation V final is equal to V initial plus AT. V initial is 0 plus A negative 0.31 T 1.2. So let's see. Negative 0.31 times 1.2. So I'm going to have negative 0.37 meters per second. Okay. And now I'll do number two. So that's how much it's moving after 1.2 seconds of pushing. Same thing. Initial velocity of the boat is zero at the beginning. It's getting pushed for 1.2 seconds. And its acceleration is 0.18 meters per second squared. Okay, so same formula. V final is equal to V initial plus AT. V initial is 0. A is 0.18. T is 1.2. Times 1.2. And then we know that after they're going to push, they're going to be going 0.22 meters per second. All right, guys, that's everything. I hope this was helpful for you, and I hope you guys learned a lot. Thanks for watching.